Okay. All right. So what we are going to start our review of image formation here by using this uh, interactive physics simulation here. And then you can take a look at the subtopic in light. Okay. And you probably have seen this before, the waves, and you can do the light. And I mean, I really encourage you guys to take a look at these. There are so many simulations in there, right, Barry, that you can, sort of like play with it and give you more understanding of what we are talking about. And what we are going to do is we can just scroll down here, just sort of like look, and then you can see that there's a concave and convex lenses. All right. So you can also play with the mirrors as well up there. All right. But we're going to focus on the lenses. And you're going to have sort of like this whole setting, just like what we did before. So you can play around with this, right? Adjusting the location of the object, the size of the object. You can just sort of like move your mouse around, all right? And you can also be able to pick the focal length, which means, here we go. So you can adjust that. Okay, I don't know which one I can grab and move, maybe on the left here. All right, so you can adjust the focal point of this one. And as you can see, it will go from having the converging lens when you have the focal point on the right. Okay, sort of remember that one, yeah. And then if you move the focal point into the other side, then that means your focal point now, it's in the same side as the object. And we said that if that is the case, that's where the light should not be, because light's supposed to get through the lenses and then just move on to the other side of the lens. But because now you have the focal point on the back, on the same side as the object, so that's where the light shouldn't be. And this is a negative focal point. Okay, so it's a virtual focal point. So as you can notice, these points sort of like, or whatever that happens on the front side of the lens, you get this intersecting between lines from the dashed line, which is just the extrapolation of the rays that actually already diverging out toward the back side of the lens. Does that sound good? All right. So I think this is kind of like fun to play with. I don't know if it's fun or not, but all right, that's what you can play around with this, adjust the focal length, focal point, whatever you like, and then you'll have a chance to check them out. Yeah, the sizing of the image with respect to the object, and the location of those with respect to the focal point, focal length, and everything. Okay, so just have that as your reference, or at least you have some simulation that you can play around and get yourself used to the whole setting over here. All right, now, so with that you can play with, then now let's get back to our handout over here. Okay, so what we would like to talk about as the last stop of this one is what happens if you have more than one lens. Right? If you have more than one lens, what can you do? Now you're going to have combinations of lenses now. All right. And we would like to answer the same question. What will be the final image? What type of your image that you're going to eventually get? Is that going to be real? Is it going to be virtual? What is going to be the image location? And it's going to be upright, inverted. And what is the magnification of the final image? Does that sound like it's a common question that you have already answered before, but we're going to do it again with the multiple lenses system right now. So what we have in front of you right now, you have two lenses now. One is lens one, the other one is lens number two. And then you place an object here, and the object is just right there. Let me highlight that for you so you can see that easily. So that's just right there. Here, that's your object. So your object is a pencil with the tip pointing downward. That's what it is. Now you place this object in front of lens number one. And the idea of the whole process of calculation is very simple. You just do just like what you did before, but now you have to do it two times, because you have two lenses. Okay, so first thing that you need to do is just figuring out where is the image from the lens one. Okay, when you have the object on your left. Okay, so you just do the same calculation, and then let's say after your calculation, you can figure out here is your image from the first lens. Okay, then you take this image and treat it as an object for the lens number 2. Does that make sense? That's it. That's the whole concept of how can you deal with the multiple lenses system here. You do the calculation one by one, and consecutively, you take the image from the first lens to be the object for the second lens. So you figure out the second image. And if you have more than 2 lenses, if you have third lens, then the image of your second lens will be treated as an object for the third lens. On and on and on. Does that make sense? All right. So over here, what you will be able to do is just take the image from the lens 1 and treat this one as an object for the lens number 2 right there. So you will have the distance away from the lens number 2, and then you use this for your calculation in step 2. And eventually you're going to arrive at your final image back then. That's it, you're done. Okay. And the good thing about this one is, if you really want to figure out the magnification, then the concept is going to be also simple as well. If lens number 1 give you the magnification M sub 1 already, so it's M1 magnification due to lens number 1. And because you already take the image from the lens 1, treat it as object for lens 2. So if the lens number 2 have M sub 2 magnification, so you can probably guess. So your total magnification will be just the product between M1 times M2. Does that make sense? Okay. So that's sort of like a straightforward extension, because it's just the magnification over magnification. So your net magnification will be just a product among those M's. So that's make it easy. The total magnification that you will get is just going to be the product of all those M's in your system, and you are done.
Okay.
Cool. However, just make sure that each one refer to the one that has a negative sign in it. So this means if you want to figure out the M1, it's going to be negative Q1 over P1. Take the negative sign with it, right? Because eventually the final sign of the M will tell you, is it going to be an upright or inverted image, which is so cool. All right. Make things very smooth, and, you don't have to go crazy about, which direction orientation of the final image should be. All you need to do is just take a look at the final sign, and then you are done. Sounds like a good plan? All right, so let's take a look. How can we really do this one? All right, so now the question goes like this. So 2 lenses, I think it's supposed to be 2 lenses, I guess. All right, that's my bad. Okay, all right, lenses there. Separated by a distance of 40 centimeter and are used in combination. The focal length of F1 is given, the F2 is also given. And because, as you can see, these two looking like a converging lens is a convex lens. So that means we already discussed this. The sign of the focal length is supposed to be positive for a convex lens. So actually, just to be sure, you can just add a positive sign in both of these lenses. Sounds good? All right, so that's done for the focal length. Now, the object of 4 centimeter high is placed 15 centimeter in front. So that 15 centimeter, it's going to be your P1 there. That's your object distance for the first lens, for the lens 1. So that's good. So it is already given there. So you can mark it like P1 there in front of the first lens. Okay. Now, find intermediate and final image distances, the total transverse magnification, and the height of the final image. All right. So the words transverse is just to sort of like just guarantee that what we are doing over here is just everything is one dimension. And when you want to talk about the size of the object, there's only one way that you can go, is the height. That's why they put the transverse magnification, because you only care about what is going on about the height of the object, all right? But in reality, of course, there will be like a longitudinal magnification a little bit, because your final image will usually get distorted, yeah? All right, but we only care about the height. Okay, so far so good. So let's get things started here. So I'm gonna color code it here. Lens number 1, I'm gonna use the blue ink, just correspond to the blue glasses that they use for the lens there.
Okay.
All right, so for lens 1, so you can list the known parameters if you want. The object distance is going to be positive 15 centimeter. Cool. The focal length of the first lens is given to be 10 centimeter, And now we know it's positive. So let me put positive 10 centimeter there. All right. Now you can figure out the image location by doing the 1 over Q1 equal to 1 over F minus 1 over P1. Yeah, I just move 1 over P1. Sorry. Move 1 over P1 to the other side. And then you can do the calculation right away. It's going to be 1 over 10 minus 1 over 15. And that is 50150, yeah? Okay. So that's good. So what I got from here is Q1 is just 30 centimeter. Perfect. So far, so good.
Okay.
So what do you mean? What you get right now is here. So you place an object here. Now you already figure out that your image, as you can see, is positive, guys. See, your final value of the Q1, which is the image location, is positive. Positive means that's where the light should be. So it means this is going to be real image. Okay, and the location of this one will be behind the lens because that's where the light should be. So that's what it is. Here we go. That's your Q1 right there. And that's 30 centimeter. Cool. All right, nice. So what we have next for you is we're going to treat this image as an object for the lens too. So you just have to recalculate what should be your new or your second lens object distance. And because they already said these two lenses are separated by a distance of 40 centimeter, so that means you already have the 30 centimeter of the image from lens number one. So that means your object distance is going to be 10 centimeter. You guys with me so far?
Okay.
Cool. All right. So that means you already know that P2, your object location, is given to be 10 centimeter in the front of the lens number two because it's still in the front. I can actually put 10 centimeter there, but we already talked about this one last time that as long as you have only single lens, your object distance is only going to be positive only, and you're never going to get a negative object distance, right? Because it's kind of crazy that you're going to have like object placed behind the lens on and on. But now here is your chance to have that negative object distance. What I'm saying is this. Think about this one, guys. Let's say if my lens number two just happens to be, let's say, somewhere here. See that? Okay. So if somehow my lens number two, it's showing up here, and you can see that the image from the first lens is already appear behind the lens number two. So as you can see now, your object location will be here. It's a negative object distance. You guys with me now?
Okay.
All right, that's the possibility. So over here now, that's answered the question that I posted before, saying that, hey, when are we going to get a negative object distance? This is when. Usually it will happen when you have multiple lenses system. I mean, you have a chance to deal with the negative object distance. Okay, cool. All right, but for our case at this moment, that's not a big deal because as you can see, lens number two is quite far away. So you don't have to worry about the negative object distance. So just to be sure, or just to emphasize that point, I just place positive sign in front of 10 centimeter. Okay, next, what else do you know? The focal length of the second lens is given to be positive 12 centimeter. Here we go. That's good. So now you can figure out the location for this image from the second lens to be 1 over f2 minus 1 over p2. Put in the numbers. Very good. Do the calculation there. Minus 2 over 120. So your final image your image formed from the second lens is going to be negative 60 centimeter, guys. So what does the negative 60 centimeter means? First of all, Ajahn, it's now virtual because it's now negative. And the negative is indicating that your image of the second lens will show up in the front side of the lens, which is right there. You guys with me here? That's your Q2. So now you understand that this Q2 right here is 60 centimeter, but it shows up in the front. That's your location of your final image right there. Huge one here. Cool. All right. But I mean, the huge or not huge, we don't know yet because we have to figure out the magnification. So let's dive into it, guys. So what else do we know? We know M1 can be calculated from negative Q1 over P1. And the Q1 is already given to be 30 centimeter. You already calculated that. The P1 is positive 15. So that is a negative 2. Okay. So what does it mean by the negative 2? It means just from the first lens, your image is going to be what? Inverted because it's negative. And it's going to be twice as big because the magnitude of M is 2. So look at this one, what happened here. Your object is right here. Now you see your image from the first lens. It's inverted and it's twice as big. Okay, so the height of the first image will be twice as big as the original object height. Cool. All right, now move on. What about the lens number 2? You do the M2 calculation. So it's going to be minus Q2 over P2. So Q2, you already calculated to be negative, right? Don't forget the negative sign there. And the P2 is given to be positive 10. Very good. So at the end, you get positive 6, guys. So what does this mean? The positive means it's upright. And 6 means it's just magnified 6 times. So look at just the lens number 2 alone. Your image from the first lens now is treated as the object, right? So object is right here waiting for you. Okay. So this is where your object is. Let me sort of highlight one more time there. Okay. So that's where your object is. And now your final image is going to be upright because we already found out that's positive, right? And as you can see, the final image still have the same orientation as the object. And it's 6 times bigger, which makes perfect. So that's mean whatever the height of that object is, this is going to be 6 times that. But then if you want to go like, okay, Ajahn, this is like the detail of each lenses, right? So this is like lens number 1 doing this, lens number 2 doing that. But if you want like a final net total, M total is going to be equal to just M1 times M2. M1 is just negative 2, M2 is positive 6. So at the end, you get negative 12. So what does it really mean? It means if you start from the original object, let me put it black here, that's your original object, your final image will be, here we go, there, inverted. See, that's a nice thing about having the sign associated with the magnification equation. Inverted, and it's going to be twice as big. I'm sorry, 12 times as big as the original height. And that's what it is. It's showing up right here. Your final image is inverted and 12 times the original height. And you are done.
Okay.
Cool. All right. So I hope just do everything in steps like this. Just do it one step at a time. Taking the first lens, do the usual calculation using lens equation, and then use the image that you get from the first lens, treat it as the objects for the second lens, and do the usual calculation again using the thin lens equation, find the final image. And then you'll be able to figure out what should be the location of your final image. And then you can calculate the magnification, M1 and M2. And then to get the final total magnification, it's just a product of M1 and M2. You can do the same interpretation that you did before. What does it mean by the negative? It means, oh, it's inverted. What is the number is signifying? It's saying that how many times it's going to get larger or smaller than the original object's height. And you are done.
Okay.
Cool, guys. So it is doable. All right. So if this is doable, then this is going to be the last exercise for this image formation stuff. But before we move on to electricity and magnetism, guys, can you sort of like think about what have you seen this system before? What kind of like instruments or optical devices that sort of like use this kind of setup? Yeah, like you have 2 lenses, You have the object, and then at the end, you look at the magnified image of the object. And the answer is very good.
Okay.
It's a microscope. That's it. Not telescope. The telescope working in the same way. That's good. All right. Your answer is also correct, except if you really want to use as a telescope, then you probably need to adjust the focal length of lens 1 and lens 2 a little bit. So you will be able to take a look at the faraway object and then give you some image for you to see. But over here, as you can see, the object is pretty close to the lens, and your final image is the magnified image. So this one is more like a microscope for this one. Yeah, and if you pick the focal length of lens 1 and lens 2 in the different combinations, you can get up to maybe like 60x. So the total magnification can go like maybe 60x or 100x. Yeah, those microscope that you probably have seen it in like biological labs and all the stuff that you did. Maybe, I don't know, have you done that before? All right, but you're right.
Okay.
The telescope also using the same setup. You have 2 lenses system as well. However, you might need to adjust different kind of focal lengths for you to be able to see far away objects better. Okay, sounds cool? All right. And I think another thing that might correspond to your actual experience in the biology lab is just when you move your slide, you might have like some bacteria, virus, or cells, whatever that you want to take a look at. And when you move your cover slide and everything up, your image of that will go opposite side. Does that, yeah? Remember that kind of thing, yeah? When you move your slide to your left, then the image go to the right. And that's because you're having the virtual image from the microscope. So it means your eyes is right here. That's your eye looking through your eyepiece, yeah, in your microscope. Okay, all right, cool. And then you might be wondering, Ajahn, if you can see, because your final image is the virtual image, and then you can only see it by your eyes, how can you take a photo of that? Because sometimes you might be able to broadcast whatever you're seeing in your microscope to maybe your TV or whatever, to your, you know, screen in your classroom, on and on. It's, the idea is very simple. Even though your light that coming out from the lens number 2 is diverging, so you can observe everything using your eyes, you can actually still redirect those lights using different instruments. Think about it. I can redirect this light and make it converge somehow. So I can steal part of this light and make it converge into a screen or CCD or whatever. And then you can use camera or video recorder to record those images and all this stuff. Okay, does that make sense? All right. So it doesn't mean that when the light is already diverging, you lose it. No, you can just still using, and it's supposed to be like maybe another mirror or another lenses, and then you just redirect everything and focus it down onto a CCD, and then you will be able to generate the image on something else that you can record anyway. Yeah, but if you just let it go, then of course the light beams are diverging. The only way that you can observe that is just put your eyes there, and you will be able to see the image. Cool. Alrighty. All right. So that's conclude the whole thing. And then we close now the second module in waves, sound, and light. Okay, everything, all the businesses, it's supposed to be somewhere around here. So I think maybe this is a good place for talking about when would you like to have your second exam? All right. So I already discussed with the section 1 about when it's what's kind of like potentially it's going to be the second exam. So if you guys still like the Saturday exam, is it still okay? Good. Does it sounds like a good day to have exam? So if you like that, I can still take the same format. If you don't have any further suggestion on anything or any adjustments or any changes, so what I can do is just the same thing, just going to release the exam at noon, and you have until midnight to submit your work. And it's going to start on Saturday, some Saturday. All right. And so if you guys okay with Saturday, so what I'm going to do is I'm going to have you guys pick the dates, and I'm going to create a poll that you can, you know, cast your votes there. And it's either going to be 12 or 19. Okay. And then and then you can vote there when you would like to have the second exam done. Sounds like a good plan here. Okay, all right. Any comments on the date and time and format of the exam? All right. So if not, then I think we're gonna stick with that format. And the good thing about that format is, which I turn to like it, in the morning. So on that exam date, then we don't have the we'll have the Q&A session just like before, in case that you want to stop by and have the last minute questions, and then that would be great as well. So if everything is just like last time, then we will not have the lecture on Saturday morning for you guys. Okay, but we will turn that into a Q&A, or in case you have any things that you want to ask. Yeah. All right. Sounds like a good plan then. Okay. All right, guys. So any questions about this module over here? Okay. If not, then let's pull up the next handout. All right. So this one is good. All right, guys. Why I'm doing this. I'm really sorry about last Saturday. That was really bad of me. I thought I already posted the announcement, and then I just realized that it's already like noon of Saturday, and then I just thought, oh my God, I forgot to post it, and I was about to do it, and I was just distracted with something else. So that's why I was just, you guys probably wondering like, what is going on with me? I just disappeared. Really sorry. I was about to do it on Friday, and I forgot, and I said, okay, I'll do it the night before, and then I still forgot it. And then Saturday, I really had to rush out, and then I had some. It's like an event or something that I have to co-host, and I'm sort of like busy with those stuff. And then during the preparation, then I saw, oh, I forgot, and then I just had to just make an announcement. But that's way too late already. You guys were just wondering where I am already. Thank you. All right, sorry guys, really bad of mine. Okay. All right, guys. So what we have for you today now, it's going to be the starting of the last module of this course, which is the electricity and magnetism. Okay. So what we have for you here, first, let me start with this. Things gonna get rough from now on. So it's gonna get, I can say it's now come back to like a more physics-ish, stuff. Then you're gonna have to deal with the vector quantity, because we are going to talk about force one more time. All right, and to get to the force, we will have to somehow come up with the idea, or come up with the theory, or come up with the way to visualize that thing that eventually will generate forces. So you're going to have to deal with something that we say it's the field. So that's a physics concept there. Is real or not, that's things to be discussed there. But at least by taking this field approach, you will be able to explain the force along with it. So whenever you talk about the force, it's a vector quantity. So the field is going to be vector quantities as well. So that's first thing, you're going to have to go back and talk about vectors. Second, now the calculus is going to be back at full force. So what that means, you're going to have a chance to do some maybe, differentiation, and you're going to have a little bit of integration, on and on. So that's okay. You guys probably prepare for that a little bit. But then the worst thing is the number 3. It turns out you're going to have to combine those two. So that means you're going to have the vector along with the calculus stuff and combine them all together. That's what we call vector calculus. There you go.
Okay.
So that's the hardest part of this one, is it's the calculus of the vector variables. So that's why things going to get a little bit crazier than before. However, we're going to confine the material that we're going to study within just a manageable, sort of like material. So you don't have to worry too much that I'm going to post like, crazy vector calculus problems. No. All right. Just for you to be able to get the idea, how can you apply those, vector plus calculus stuff and use that in the electricity and magnetism topics. That's all I care about. I think you just have enough sort of like experience or enough exposures using calculus with these theories, and that's good enough. All right. So don't worry about like super complicated problems or anything. I don't have the intention to do that. All right. But I mean, the key is you have to have some experience with this. It's college physics after all. All right. Okay. So what we are doing today is this, guys. We're going to start talking about the origin of this force and the origin of this field. And it turns out to be charges. Every time you talk about charges, you should think of mass. That's my approach to this one. Every time you talk about mass, it's kind of like very familiar because you probably studied this kind of thing so many times since, you know, middle school science, the elementary school science, on and on. But then the thing is, the nice thing about doing this kind of comparison is this. The comparison is actually very close. In the mass stuff, in the masses business, you also have the field defined. I don't know, have you noticed that before? But this is what I'm going to show you right now. Yeah, this is the mass. My mouse here is the mass. And I'm just going to let it go. And everyone knows it's going to drop down to the floor, correct? No big deal. That's what it is. Mass is mass. But once you place inside your gravitational field, everyone knows, Ajahn, there is a G going down. So if you have a mass inside this gravitational field, it will experience the weight equal to mg. Everyone agree with this equation? You have used this so many times from Newtonian physics, Newtonian mechanics, and all this stuff, right? Charge will do the same thing. So what I'm having here for you is you're going to have that fundamental stuff that intrinsic to materials, objects, particles, or whatever that we're going to name this charge. And it turns out this charge will interact with another kind of field. It's not gravitational anymore, but now it's going to be electric. So that's why you can imagine that there will be something that we're going to name it electric field. Field. There will be some field there. And the concept is going to be exactly the same. If you have a charge inside an electric field, it will experience an electric force. Let me put that subscript E for now, just to emphasize that you will get the force due to the field, just like what you had weight due to the gravitational field. So you guys good? So that's why I'm saying that you're already familiar with this concept. If you think back in the day of gravitational stuff, it's already there. So the field and the force will come hand in hand. That's nice. Okay. And to be able to do the numerical calculations and everything, you need a law. So eventually that will lead you to the law that governs this whole thing is called Coulomb's law. And this law will be equivalent to the gravitational, universal gravitational laws or the stuff. So you probably have seen this G M1 M2 over R squared. Yeah, that's the attractive force between two masses. And then you have the Newton's gravitational laws talking about that attractive forces. It's right here. You're going to have that kind of thing that look exactly just like that to describe what will happen between those charges. So cool. So that's the whole idea. And to me, it's pretty, well, straightforward if you remember how to compare this whole thing with the gravitational business that you did before. Things will be straightforward there. But if you sort of like, you know, take this one as like a new concept, this one is electricity, and then you're going to see magnetism, and things will go crazy because it seems like, hey, this is new. But it turns out, no. The concept of field is already the same thing. I mean, it's this field anyway. So it's just a matter of the shape or the form of the equation that's linked between the force and the field. But the concept of the field itself is going to be exactly the same as before that you saw from gravitational calculation. Sounds good? All right. So it seems like, okay, it's pretty doable. It's pretty doable. All right. So that charge that we talked about there, it turns out that's pretty much responsible for everything around us, believe it or not. And this is kind of weird stuff. And well, of course, you don't really know why per se, why we have this kind of thing in our universe, but it's already here. And one thing that you probably sound like learned from so many places, atoms, right? The building block and that fundamental units of stuff that build up elements, build up material, build up compounds, build up molecules, periodic tables and everything. So you have the center of atoms made of something that is positively charged. Yeah. So you have proton in there. You might have some neutron in there, but net charge is positive. So that's the charge is there. And then you said you have electrons that orbiting around. The electron itself is negatively charged. So the complications that you have with this business is just now you have two types of charge, positive and negative. You never had that with the mass. The mass is mass. When you have two masses, they're going to attract. That's it. There's no other choices. But here you have two types. You have positive charge and you have negative charge. And then there are some, options for you now. They do not always attract. They also repel. There is a possibility of repulsion force. So that's why we have to come up with the way that we can describe the whole business here, right? Not only just the attractive force anymore. Cool? That's what we're trying to get to. All right. So we have two types of charge. One is positive. That's, we named it. All right. Actually, you can name up or down. You probably have heard that from chemistry. There's a spin up, spin down. Or you can say it's a north and south. That's what you call the magnets, right? There's a north pole and south pole. But for the charge, yeah, Benjamin Franklin did it. So he just assigned one type to be positive, the other type to be negative. So if Benjamin Franklin decided to call one type like A type, the other one is B type, so you probably have A and B charges. But okay, positive and negative is already stick with us right here. So you either have positive charge or negative charge, okay? But the funny thing about this one, and I think I have to mention this a little bit before we move on to the real calculation here, guys, the unit of this one, all right, so we're gonna honor Coulombs who give the law of this one here, that's the unit of charge. So think about this, the Coulomb is the unit of charge. It's gonna act in the same manner as the kilogram for the mass. Does that make sense? Okay, so just to make the comparison complete. So the amount of charge is in Coulomb. The amount of mass is in kilogram. So in terms of the role of the unit, Coulomb is behaving just like kilogram in gravity. Okay. Next, second thing is the amount that we're talking about, it turns out to be a discrete number. Isn't that weird? Whoa.
Okay.
This is not normal. It turns out, if you talk about electrons, you guys familiar with electrons? Yeah, a little bit. And if you take a look at the amount of charge that electron intrinsically carries, it turns out that the amount of charge inside the electron is this numbers right here. It's 1.6 times 10 to the negative 19 Coulomb. But what is weird about this number is this. It turns out everything in this universe will carry the charge as the multiple, is an integral multiple of these numbers right here. So that means in this universe, guys, you will not see any particle carrying a charge of 1 point, let's say, for example, 1.7 times 10 to the negative 19 Coulomb. No way. You're not going to have like 1.8. No. You're going to have like smaller than this. No way.
Okay.
This is the weird one. So what we're saying is it turns out the charge around you, let me throw the word here, quantized. So this is the one that is going to have some, reference from the quantum physics and other stuff. So the quantized is just mean it's a discrete value. It's jumpy. It's like, it's going in steps. It's not like a smooth number. So that means you don't have liberty of picking any numbers for your charge. No, you cannot. It has to be multiples of this number only. This is so weird, right? And the reason for that maybe is just part of it is responsible for the electrons. Electron is just super fundamental particles in our universe. And it seems like it's just so hard for you to go beyond this, even though you might have heard of, maybe some of you have heard of like fractional charge, like in quark and other stuff, but that is way deeper, and you don't have like any like stable particles that carry the charge smaller than this value over here. So you can take this electronic charge, that 1.6 times 10 to the negative 19 Coulomb, to be another fundamental constant of, you know, physical parameters or physical constant that you can use. Yeah. So we can use E for that. So everyone seems to agree to use E for electronic charge. Okay. And just for the electron itself, the charge that this electron carry will be that negative E. So it's going to be negative of that 1.6 times 10 to the negative 19 coulombs right there. All right. So that's good to know. Okay. And just don't have to worry too much because that negative 19 is super, super, super small. So for our everyday's experience and everything, you feel like it's pretty smooth already, because it's hard to imagine any quantities that can have numbers that low. Even though you have like nanotechnology, nano is 10 to the negative 9. If you go pico, it's 10 to the negative 12. If you go femto, it's like negative 15. So that's down to the nucleus already, like the nucleus, the size of the nucleus in atoms. So 10 to the negative 19 is pretty small numbers. All right. So you can feel all right for now. So there's a question comes in. So nothing can have charge less than E. Correct. That is right. Yeah. So true. Yeah. So the best that you can do is just, you probably just like exchange one electron, for example. So if you lose one electron, you will get more positive because the electron is negative. But if you get one electron deposit on you, then you get a little bit like that much, negative 1.6 times 10 to the negative 19 Coulomb negative on you. Yes. All right. And one final conclusion is everything around you in general, they are neutral. So you have the same amounts of positive and negatively charged in that material. So if you don't have any, you know, some weird condition, it doesn't have to be weird. If you don't impose any condition on materials, everything seems to be neutral. Like the mouse over here is neutral, right? And when it's not neutral, you might get like static charge, like, you know, get zapped a little bit. That's from static discharge and stuff like that. So that's could happen, especially when you have like a dry day, and then you have like your clothes is just rubbing against each other, and then you lose some charge, or you gain some charge a little bit, and then you know, close by, then you get zapped and all this stuff. So that's electrostatic discharge there. All right, but in general, things are neutral, so that's pretty cool. All right, yeah, that's kind of nice. So if not, then your life will be crazy a little bit, right? You get charged all the time. All right, guys. So with that in mind, then the idea will be this. So when you have two types of charge, positive and negative, so the rule, it's simple. If you have the same types of charge, they're going to repel each other. If you have the opposite types of charge, they're going to attract. So this is an extra condition that you add on top of what you had with the gravitational attraction. So you have a chance of having the repulsive force now. Depends on the types of charge. Sounds good? All right. Okay. So that's what it is. And once again, just want to emphasize, when you have a positive charge here on glass, usually it's just what I just said. It means that you probably lose electrons there. So the glass that's supposed to be neutral now turns positive because electron gets sort of like, you know, escape from the material. All right. And plastic might have more ability to attract electrons, so electron might just deposit on it. So you get net negative material. So that plastic can behave like a negatively charged material, and then it will attract, or it will get just, you know, interact with the positive charge material by having the attractive force. There you go. All right, guys, cool. So this gives you a overview of what business we are going to deal with. We're going to deal with charge, we're going to deal with fields, we're going to deal with force, and we are going to talk about how can we calculate the magnitude, directions, and everything of this whole electric charge business here. All right, guys. So I think this is a good place to stop, take a quick break, and after the break, we'll dive into how are we going to calculate all this business here. Yeah. All right, guys. Take 10. I'll see you around 11. Yeah.
Okay.
All right. So what we have, okay, before we move on, all right, there's a quick mentions. I would like to quick mentioning about this classifications of material around you, and then I will give you the connections of what we are about to probably face in the future. It's all about the movements of the charged particle in the material. So if you have the material that allows the charged particle to travel pretty easily, such as, for example, you probably can figure, sort of like, have seen this before, all those metals allow electrons to move pretty easily, or seawater, that's like a salt water, you have the sodium chlorines and all this stuff here. So you have a sodium ion and a chlorine ion that can travel easily in the solution. So we're going to call those conductors. All right. So those are the stuff that can have the charge travel pretty freely in that material. On the other hand, in the opposite case, you might have something that do not allow charge to travel very easily at all, such as like you have rubber, glass, diamond, wood. Okay, these kind of things that you kind of know. Oil is a liquid, but it doesn't really conduct really well. So those class of material, we will call them insulators. Okay, and of course, you're going to have something in between. That's you have material that's somehow almost a good conductors or almost a good insulator. So it's sort of like somewhere in between. So if that is the case, you are talking about the semiconductors right there. But the good thing about this semiconductor is after the invention of transistor or the stuff, it's just this type of material allow you to manipulate the property of the material. So that means you can turn this material into conductors, or you can turn this into an insulator. So now when you have a way that you can control, so that's when you start to do some logic there. Does that make sense?
Okay.
So that's mean you can say, okay, yes, you can go, or no, you cannot go. So now you start to be able to have a device that allow you to make decision. Yes, no, 0, 1, true or false. And that's the starting point of a digital age and everything. And once you have those transistors that have this kind of ability to, say yes, say no, start to do some logic there, and then you put billions of them in one place, and then you can start to doing some complicated logic there. And that's the starting of central processing units, the CPUs, and all the stuff that you use every day in your chip. That sounds good. All right. So those are the stuff that's the sort of like the beginnings of everything is electricity and magnetism theory that we are about to study right here. All right. So how can we calculate that? Okay. So I would like to make a quick statement first. The approach that I am about to introduce to you, I would say it will look a little bit different from what you might see from the textbook, even most of the textbook. And I'm not so sure why, but the idea is this. In the textbook, they will try to introduce the electric force first, because maybe that's the easiest way to get you into the story, right? Because you guys familiar with the forces already. So to start with force seems to be a logical way. And then they will start to talking about the Coulomb's law that explain how can you calculate the force magnitude, like how big is the force acting between charges and all this stuff. And then they will introduce electric field. Okay, and then it was just, okay, recalculate everything, but now we talk about the fields alone without the force. And then they will talk about the connection between the field and the force, and then just wrap up the whole business here. To me, it seems like, and it's been like this for all my life here, it's just like the field and the force are pretty much interconnected by itself by definition. When they say by definition, if you look at the first equation there, I'm just showing you the definition of electric field. And if you look at this equation, how do you feel? Okay, first of all right, electric field is a vector quantity. The force is also vector quantity, but then it's just the force per unit charge. So that's why I say field and force are exactly the same thing. It's just you define it per unit charge. You have already done this before. So if I write this equation on the side over here, guys, weight is mass times gravitational field, gravitational acceleration, G. I can actually write this equation like this. The G that you're familiar with, 9.8 meter per second square, blah, 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 is just the weight over mass. Does it, do they look the same?
Okay.
Yeah. So that's why I'm saying that if you study field, you will automatically get force. That's how easy it is. Okay, guys, with me? So that's what I would like to show you here is I'm going to teach you the field first. Once you get the field, the force is going to be just a piece of cake. You just slap the charge in there and then you get the force. What else could it be? It's just the charge times the field. Just like you have the mass times the G. Same thing. Okay, you guys with me here? Okay, so this is what I'm going to do. Look at this two figure here on the right. So what you're seeing over here is this. You have first, let me place one charge there. So let's say my charge here is fixed and it has the amount of charge Q on it. Okay, cool. All right, so I have a fixed charge there. Now I bring in another charge and this one has Q naught charge on it. So the knots there just saying that in the textbook usually will refer to this one as like a test charge, but it can be any charge. It does, I don't know what charge, whatever you just bring in. So you bring in Q naught charge here, and let's assume that this one is still positive for now. Okay, so according to the law that we are about to study, and the one that we already mentioned briefly, that if you have the same type of charge, they are going to repel each other, right? But because the charge on the left is being fixed, maybe you just, put it on the table or something like that. Okay, it is fixed. Then if you're focusing on just the Q naught charge there, that Q naught charge will experience the repulsive force F away from the Q charge on the left. You guys with me so far here? All right, now that force can be calculated using the Coulomb's law, on and on, but that's not the point at this moment. So what I'm going to do is this. Instead of having you to calculate the force right now, what you can imagine is this. But Ajahn, let's forget this one for now. Okay? When I say forget it, you just erase this from the whole thing. So forget that you have this charge right whatsoever. Nothing. Okay? And then you imagine that what is happening here at point P, the point that you about to place the Q naught charge here, but you haven't done that yet. Let's say that this is just a blank space at this point. And then you turn our attention to calculate the field at point P. You guys with me? So it's bring you down to the bottom figure over here. So instead of calculating the force right away, you are going to calculate what is going on at point P in terms of the electric field first. So let's say you calculate the electric field and you get the field at that point to be vector E over here. And once you know the field, then I can actually bring back that charge, place it there, that my Q naught charge, and I can tell right away the amount of force that acting on this charge is going to be Q naught times E that you just calculated down here, and you are done.
Okay.
Does that make sense, this process? Okay, one more time, and just give you an comparison here. I have my mass here, okay, that's my mouse. I know if I let it go, it's gonna drop down. That's because at this moment over here, there is a pulling down force, try to pull this mouse downward. That's the weight, which is the gravitational force, okay? But instead of having my mass right here, I just take it out. And what happened right here in my forehead here, you guys already know there is already a downward gravitational field at this point around here, space around me, there's already G pointing down. Okay, so all you have to do is just place the mass in the field. That mass will experience the force equal to what? The mass times the G, mg, that is your weight, the gravitational pull. Everything must be exactly the same here. So for you to calculate the force acting on a charge at point P here, all you need to do is first calculating the E. What is the field at that point? And once you know that, by placing the charge there, the force will be simply just Q times E. And you are done.
Okay.
Okay, this is a whole process that I'm going to introduce to you in this direction. Does that sound reasonable? All right. And that's why it's save times, because you will understand field and force at the same time. And actually, the calculations are going to look almost the same. Yeah, because field is just a force per unit charge. So they're going to be different by just the amount of charge that you multiply in the front. That's it. Okay. So there's a question comes in, the test charge must be 1 Coulomb. No need to be. Don't need. It can be any coulombs, but then by definition of the field, you're going to have to divide it out. So it's going to come down to 1 Coulomb anyway. Does that make sense? So if you place 1 Coulomb there, so that's good. So that will turn into number 1. So the field is going to be equal to the force. However, if you place Q0 Coulomb in there, whatever the force that you get, you have to divide it by the charge, then you get the field. So I don't know what that, like my answer go into a loop or something. Right, but the test charge can be any value. Yeah. Yeah, but if you take it to be 1, the force that you experience will have the same value as the field at that point, if you pick 1 Coulomb charge there. Does that make sense? Okay. All right. Okay, cool. So with that, then how can we calculate the field? It turns out the equation that allow you to calculate the field will have the form that looks like this, but we'll come back to that. All right. We'll get something else first, and then we're going to slap the equation toward the end. Okay. So this is what is happening here. Bajan, we have 2 types of charge. What you're talking about over here is just all positive charges. What happens if you have a negatively charged particle? So let's look on the right. Things will go exactly the same, except you just have to give like agreements, or have to take some convention about the direction of the field that coming out from the negatively charged particle. That's all you have to do. What I'm saying is this. So think about, again, if I replace my fixed charge to be negative instead of positive. I had positive before. Now what if I have a negative one instead? So now the charge that is fixed here is now negative. And I still placing the same Q0 charge, which is still positive there, right? We already agree that when you have the opposite charge will attract. So that means the force that the Q0 charge is experiencing is going to have the direction point towards the Q. It's pulling in. Yeah, it's attractive. Cool. All right. But then you're going to have to do the exact same way of thinking. If you want to go through the field first, you just have to eliminate this whole eliminate. I mean, you don't have to worry about the charge that you're going to place there at this point. So I'm just going to sort of like, okay, I'm going to remove this, forget about this force at this point. Okay, right now. And then what I'm going to do is just try to say, hey, what is happening at point P first? When I say what's happening is I want to calculate the electric field at this point. With me? And now, because you want at the end the force to be pointing towards the negative charge, you have to agree that the field has to point inward, like so. You guys with me? So these two will look exactly the same. Yeah, there we go. So final agreements, I mean, the conclusion, the final conclusion about this one is, if you have a positive charge generating the field will point outward. Here we go, outward. okay? And if you have a negative charge generating the field will point inward toward the charge. So you can think of the charge that generating the field to be the origin of the field. But if that origin of the field is a positive charge particle, then the field is diverging out. So it's just like radiating. It's like, it's not animation or anything, it's there, but it's just in the direction that's coming out from the positive charge. And if it's negative, the field just point towards the negative charge. Yeah. All right. So what you have is this figure over here. This is the agreement that we have. Okay, the question comes in, can the test charge be negative? Yes, it can. Test charge can be positive or negative. And the thing is, at the end, you're going to have to divide that amount of charge out. So I think that is okay. Yeah, but it's just taking test charge to be positive, it seems to be more natural or easier for you to, derive the equation or understand the normal case or the initial easy case that you can agree with positive numbers everywhere. So it's kind of easier for you to get the whole concept. But you can replace everything with negative and everything still will be fine. Yes. Yeah. Okay. All right. So this figure over here is showcasing what does it mean by field around positive charge. This on the left, fields coming out from the positive charge. And if you look at the negatively charged, the field will try to point towards it. All right. Okay. So speak like sort of like loosely. On the left, the field coming out of the positive charge. And on the right, the field is sinking into the negative charge. Something like that. Yeah. Okay, so with that in mind, all right, in general, you will have like combination of charges, any arrangement of charges will be, you don't know. So the fields that coming out of it as a net summation of all of those electric field around those charges, you can name it the electric field lines. So these lines will give you the idea of what is going to be the directions and the magnitude of the electric field. Does that make sense? Okay, that's very good. So that means in general, what you can have the line that might curve, might, go somewhere, just like the figure on the right. So these are the electric field lines. But one thing that you probably can intuitively get, if I'm asking you, do you think the cross-sectional A and the cross-sectional B in comparison, which one should have a stronger electric field? What do you think? Just by looking at this and just get the sense of this one. So you think which one should have a higher electric field strength or the magnitude of the field? Which one should be stronger? Well, yeah, everyone seems to agree, right? Because it seems like the line is pretty dense. The density of line seems to be high on the cross-sectional area A. But on the surface B, it's kind of like, sort of like spaced out. So it's kind of like, all right, it's kind of weak. So that's what it is. So the density of electric field lines, so it's the number of lines per unit area, will eventually give you the strength of electric field. That's cool. So that makes sense on this one as well. See? So when you are close, very close to the field, if you have a cross section over here, yeah, that's kind of like, okay, that's kind of a lot of lines going through this area. But if you move that area outward, you can tell that the number of lines will be a little smaller, or maybe not a little, it's going to be smaller. So you can say that the electric field closer to the charge should be stronger than the electric field that already far away, which makes perfect sense. Yeah. So there are some connections about the density of electric field lines per unit area and the magnitude of the field. That will be another thing that we're going to be able to calculate as well. But for now, it seems to make sense that electric field strength should be proportional to the magnitude of the charge that's generating the field. That makes sense. Well, then if you bring in the bigger charge, then you should have a stronger field. That's fine. And the second thing is, it should be inversely proportional to the distance from that source. Because, all right, if you have a charge and if you go further away, electric field should be weaker and weaker as you just move away from the source. However, from the experiment, it turns out this inverse proportional is going to be square function. So it's an inverse square relationship. Cool. All right. So that's what it is. By knowing these two, now we can conclude this equation right here. Electric field, by definition, is just the force, electric force per unit charge. And then you can calculate using this law. Actually, this is a Coulomb's law. It's a K, the constant shows up. All right. And this number is just fixed. And then I can give the number roughly for you is about 9 times 10 to the 9th, -9. And the unit is going to be a little bit crazy, but you can just move things around. It's going to be like Newton meter square per Coulomb square, on and on. All right. But anyway, it's just a fixed constant. Okay. And now you have the charge, because the bigger the charge, the bigger the field. So the charge popping up there in the top. And it's inversely proportional to the distance square. So that's it. E equal to KQ over R square. And this make physicists like dream about the grand unified theory, because if you look at this equation, well, Ajahn, it looks so close to what you probably have seen before from F equal to G, gravity universal constant, M over R square. Looks so close. Very nice. Okay, so that's why it's like sort of like, okay, there is like this universe has some common structure somehow, from gravity to electricity, and then eventually we're going to do magnetism and all this stuff. All right, but up until today, that's not completed yet. We still don't have the grand unified theory, one theory to explain every physics in this universe. So it's not that easy. All right. Okay, so that's a Coulomb's law, guys, but it's a Coulomb's law in the form that allow you to calculate the electric field. All right, and in combination of this, you will be able to calculate force automatically. Okay, all right, KQ over R square. Now, here's the annoying parts, guys. You seen this? The R hat. This is the annoying one. What is this R hat? The R hat, the hat suggests that it's supposed to be a units vector. The reason I say suggests because you're probably familiar with the hat unit vector from the I, J, and K hat. Do you guys remember this? All right, so these are the units vector that pointing along the X, Y, and Z axis. Okay, so if you remember that one, right, you have X, Y, and Z. You can have like I hat pointing along the X, J hat pointing along the Y, and then K pointing along the Z. That's an IJK. But the thing is, this is a different stuff. You imagine the I hat vector. It's pointing in the positive X direction all the time.
Okay.
Does that make sense? All the time, because X, positive X is always pointing to maybe your right-hand side all the time. So the I hat will also point in the positive X direction, which is pointing in your right-hand side direction all the time. But this is not that hat. Is the R hat, and the R is the radial vector. Is the units vector that points in the radial direction. This is annoying a little bit, but that's not so bad. Here we go. Look at this. When I say radial means there must be some sort of like a center of the circle or something, like the center point, and then everything just radiating out. That's why we call it the radial, right? So the idea is whatever that point in the radial direction, that is your R hat. Yeah. So that means you can also have this to be R hat as well. Down here is R hat. There's also R hat. Whatever that point in the radial direction, they are all R hats. So the R hat is just saying that it's point in the radial direction. There is a common center. And as long as you grab that as your center, everything that radiating out from that center, those are called radial direction. And you can assign the R hat to all of those radial directions. So this is a unit vector that doesn't have a constant direction. It doesn't have the fixed orientation in space. Okay, you guys with me? The IJK has a fixed orientation because it's pointing along the X, Y, Z axis. And X, Y, Z axis doesn't have any other orientation except just X, Y, Z orientation, right? It's just, that's it. It's just gonna point in the single direction all the time. But not for the R, because the R is a radial direction. So you have what spherical shape side. I mean, you can radiating in all directions. So those are called R hats. So this is an annoying one, right? But that's the device that mathematics gave us, allow you to define a vector in the radial direction using the R hats there. Okay, maybe it's my explanation is a little bit too long, but this might give some of you some confusion about the R hat. So that's why I spend time try to explain what does the R hat mean first. It's gonna pop up from time to time. All right, guys. So with that, along with our agreement, so I hope now you understand what it is about the field, the force, and the R hat, and the equation that governs how can you calculate the magnitude of the electric field. So let me recap. All right. Electric field from the positive charge will radiating out. Electric field from the negative charge will converge in. Cool. All right, just testing by placing any charge there. If that charge is positive, yeah, let me put a charge Q naught in there. And then Q naught, if it's positive, right, I'm going to get to the negatively test charge there, yeah? If that is a positive test charge, it doesn't have to be test charge. Let me say I've just placed a charge there. There's a positive Q naught charge being placed there. First thing first, see, before you put that in, at this point, you already have the field pointing outward. You guys with me? Cool. Because you have a positive charge right here, the field is going to point outward. How much? K. If this one has a charge Q, is Q over. Now you take the distance over here. Let's say if it's A over A square, and it's going to point in the radial direction there. That's your R hat. Okay, don't put it there, but that's a radial direction. So you put R hat there, and that's good. All right, that's the field at that point. So I can mark this to be point P, for example. Okay, and now you place a positive charge there, Q naught positive. It will experience the force equal to Q naught times the electric field that you just calculated down here. And you are done.
Okay.
Cool. All right. And now that concludes that, okay, Ajahn, you have a positive charge there. When I put a second positive charge there, it will experience a repulsive force. See, the green vector is pointing out away from the charge that's down there. Okay, let's look on the right side. Now, if you have, actually, we can look at the left. So what if I place a negatively charged instead? I'm interested in this point. Let me put point Q. Okay, electric field at that point pointing outward. So that's your electric field. You guys with me? Cool. All right, electric field pointing out. Now I place a charge here, and the charge has a magnitude of Q. And now I want it, I'm sorry, that's not charge, that's a location. That's a charge Q naught, and that's a negative. So I want to place a negative charge at that point, at point Q. So from the equation, force equal to Q times E, right? That's how simple it is. So what I'm going to have to put in is a negative Q naught E. You guys with me? It's a charge times the field. So when my charge is negative, negative sign is going to be there. And the negative sign in the vector equation means it's going to point in the opposite direction here. Wherever the E pointing to, the F will point in the negative direction, opposite to the E. So this is a reason that you will get the force acting on this negative Q naught charge to be pointing opposite to the E. See? Cool. So that's why what I'm saying here is the equation that's saying that force equal to Q times E is very good. It's universal.
Okay.
It works. No matter the charge that you put in the position of the field is going to be positive or negative. What it says is just saying that if the field is interacting with the positive charge, the force will point in the same direction. But if you place the negatively charged in the field, that negative sign there will say the force is going to point in the opposite direction to the field. Does that make sense?
Okay.
Okay. So that's what it is. So that's conclude that y, you can place any charge there, and the equation of force equal to charge times the field works in all cases, all the time. Cool. And the conclusion that you get from here is just a simple saying that you have a positive charge, and now you place the negative Q naught charge close by. That negative charge will feel the attractive force. See, it's going to move towards the positive charge on the left. Nice. Okay, any questions so far? All right, but the business is going to get complicated because of the vector nature of these fields and force. Okay, all right, guys. So what if you have more than one charge? I mean, actually more than two charges, actually, in the sense that if you have fields that get generated from system of charges, you have a bunch of charges that you want to calculate the electric fields form, then what is going to happen there? So all you need to do is just take the summation of all those stuff. However, the summation has to be the vector sum because you are trying to add vectors together. Okay, so that's, you can take things that you have already sort of like a practice back in the Newtonian physics day, adding vectors, breaking into components, do x-axis combination, y-axis combination, and recombine everything. Everything works because this is just the vector summation there. All right, and if you try to combine those stuff all together, and then you can rewrite your electric field lines, then you might find this is going to be your net electric field lines. All right, but don't worry, this is the work for like a software or whatever. We're not going to be able to do this by hands easily. So let's just say that the key concepts is electric field is going to come out from the positive charge and it's going to converge into a negative charge. Okay. All right. Very good. So let's take a look at some examples, shall we? And that will allow you to see how can we work using the Coulomb's law. So you have three equal positive charge Q are at the corners of equilateral triangle of side A as shown. What are the magnitudes in direction of the electric field at P due to two charges at the base? All right, you want to give it a try?
Okay.
So the key is very simple because you want the electric field at point P. So actually you can just get rid of the charge at point P because this is inconsequence. I don't care. All right. And you forget about the charge generating the fields at the location of the charge itself. We don't talk about that. So that means, what if I put the R in this equation to be 0? Like I want to calculate the electric field due to itself. No, we don't do that. All right. So we don't have that kind of thing because at the location of the charge itself, you can think of it like a singularity or something like that. So we don't deal with that yet. Like for example, we don't know the size of electrons. Electron doesn't have like a radius. It's not like a bead, or it's not like I don't know. It doesn't have sizing. Yeah. So we don't talk about what is going on it. Okay. So all right. So this is what we have. So we can just ignore the charge on the top one, and then we just asking, hey, what is the electric field at point P? Okay. So what you can imagine is this. All right. Let's start from the left positive charge Q. So what you are getting here is you just have to imagine, all right, just in case that some of you still confusing, don't forget the electric field is always there. So let me write it like that. It's positive charge, right? So it's going to go all the way like this. It's already there around the positive charge. Okay. But all you care about is just what is going on at point P. So you only care about what is going on at point P. So at P, it's positive charge. So you will get the electric field pointing away from it. You guys with me? Cool. All right. Now move on to the right side positive charge. The one on the right will have its own field. Okay. It's no big deal. Everywhere. Just keep going. Everywhere. Spreading out. Everywhere. But what we are looking at or care about at this point is what's going on at point P. So you're going to get the electric field pointing up like so. Cool. All right, then now okay, let me write it like have like a good sizing here. Now what we have to do left is just add these two together using the vector summation. All right. So what we're going to do next is, okay, John, let me call this E from the left. And I'm going to call that E. That's from the right. Okay, cool. So E from the left, now you know the direction. What you need to calculate next is, what about the magnitude, John? Okay, so that is your electric field vector is pointing in that direction. I want a magnitude. And sometimes, because you might not want to, write that notation too long, I can just say that it's an E sub L and then you're done. So without that arrow sign on top, you already say this is the magnitude of that vector. All right. Or if you want to be like super clear, you just say, hey, this is a magnitude of this vector. That is fine. These two are exactly the same notation here. And from the Coulomb's law is going to be K, the charge that's generating the field over the distance square. And as you can see now, I don't really have to do any vector calculation anymore because I already done with the direction. My direction is already there. So all I have left to calculate is just the magnitude. So the magnitude of R hat, this already turned into 1. So that's why you don't have to worry about that R hat anymore here. Is it good? All right. So keep going. So I just substitute in the value. The charge is Q. The distance is just A. And that's it. That is my magnitude of this E sub L vector. I'll do the same thing for the E sub R vector. So it's going to be K, the charge generating the field. The distance away from the source to the point of calculation is also A. Whoa, so that's good.
Okay.
So it seems like the magnitude of these two vectors are exactly the same, except they are pointing in a different directions. So what is going to be your net vector sum? Well, no problem. Let me split them. The E sub R can be split into two components, vertical and horizontal. And because this is equilateral triangle, I know this is going to be my 30-degree angle there. So I can place 30-degree up top here. Okay. So that means whatever on top here is going to be my ER cosine 30. Cool. I'm going to do the same thing for the green vector. I can decompose that into a vertical, horizontal component. I can get rid of the original. Okay, the angle stays the same. This is 30. That is also 30. So my vertical component of the EL is also EL cosine 30. And because I know these two vectors have exact same size, okay, so now I can say, oh, Adan, that horizontal component must be canceled perfectly. So you're only going to have net vector to be pointing upward. Cool. All right, so I can work that. Net electric field is going to be just the ER cosine 30 plus the green component that's point vertically, EL cosine 30. Cool. Nice. But then because these two are exactly the same size, I know it's going to be KQ over A squared. Cosine 30 is going to be root 3 over 2 and then multiply by 2. Because they are exactly the same. 2 cancel and you are done.
Okay.
If you want to write this one down in terms of a vector final equation, final answers, you can say, hey, put the arrowhead on top. And I just say it's just that sigma E that you just found. And I just say J hat if you like. If you don't like the J hat, but Ajahn, I'm not defining any X, Y just yet. You can just say delta E. Sigma E pointing up. It's good. All right. Or you can even just say it's sigma E pointing upward. F is fine, right? Because to define a vector quantity, you need magnitude and direction. That's what you have. See, not bad. Is it doable? Yes, yes, yes. All right. So if this is not too bad, let's do one more, shall we? All right. Just like just one more exercise, and I think we're done for today. I think this is it heavy enough? All right, guys, let's do one more. It's the same type of question, but now you have more like numbers and numerical values that you have to plug in a little bit more. The figure shows two charged particles on an x-axis. There's one negative Q, given a number there, one positive Q on the other side. They are at x equal to 3 meters to the left and to the right. What are the magnitude and direction of the net electric field produced at point P, which is 4 meters high from the origin along the y-axis? You want to give it a shot, yeah? Well done. Just finish it, yeah? จะได้ไปนะ Okay, you guys give you like a 1 minute head start here. Like slowly think about it. Just make sure that you sort of like follow the whole logic that we have been building this lecture here. Start from the left, shall we? Negative Q. Okay, around the negative Q, you will have the electric field around. So here, let me give you a guideline here. All right, so that's a radial direction. Okay, and because this is a negatively charged particle, you will generate electric field points towards it. Cool? With me here? All right, electric field at point P will be pointing towards the source. The source right now is the negatively charged Q. So let me name this vector to be E minus then, because that's the negatively charged minus Q that is generating this field. I can calculate the magnitude of this one right away. It's going to be K. The charge generating this one is the Q over the distance from the charge to the point P, because they already told you that this is 3, the height is 4, so you know this is going to be 5 from the right triangle here, so it's going to be 5 squared, and you are done.
Okay.
One thing that you can notice over here is when I plug in the Q value here, see, I don't need the negative sign anymore. You guys with me? The reason for this is because that negative charge, negative sign over there just told you that the E is supposed to point towards it. That's my point. But once you're already figuring out the directions of the electric field, the rest of the work has to be just finding out the magnitude of that field. So that's why in this equation, I just take the magnitude. I don't have to worry about the negative sign anymore. Cool? All right, then try again, guys. On the right, you have a positive charge Q generating the field at point P. I'll just give you a guideline here. There's a charge generating the field. That's my radial directions. And now because it's a positive charge that is generating the field, so the electric field at point P is supposed to point outward. There you go. You guys with me here? Cool. Nice. And I can also calculate the magnitude of that E positive. Let me name this E positive vector to be K constant times the Q that generating the field. It is just positive Q, but I don't care positive, negative. I just say it's Q divided by, once again, the separation from the source to the point of calculation, which is still 5 squared. Once again, they are at the same size. That makes sense because they have the same magnitude of charge, same distance away from the source charge, and that's it. So the electric field is supposed to have the same size as well. Nice. Okay, very good. Now, you just do the vector summation one more time. All right, so the E plus, I can split them into 2 components just like before. Okay. And the E minus, I can split them into 2 components as well. Same thing here. But because the blue and the green are arrows having the same length, so now you can conclude that the vertical component must be perfectly canceled each other. So you only have the horizontal components of the electric field that you need to add, which is quite all right, because if you define this to be theta, so that will be theta as well. So what you want is the horizontal component of the E plus is going to be E plus sine theta. The horizontal component for the green is going to be E minus sine theta as well. You guys with me? All right, and let me put theta here as well. All right, and that will allow you to find out the net electric field at point P. I can put P down here, is going to be E plus Sine theta is the opposite over hypotenuse there. It's going to be 3/5 plus E minus sine theta, same value, 3/5. And you're almost done here. So at the end, you're going to get twice the 3/5, and then just take one, E K Q over 5 squared. And you are done.
Okay.
To put this in the vector format, the net electric field at point P vector is going to be, okay, let me work this thing around. It's going to be 2 3/5 K 9 times 10 to the negative 9 over 5 square. And the charge that we're talking about is this big, 3.2 times 10 to the negative 19 Coulomb. And you can say negative I direction. I put negative I hat there. Or you can just simply say it's point to your left and you are good to go.
Okay.
Not bad. It's quite doable, I guess. Yeah. So I think maybe the hardest portion of this introduction of the electric field is just a matter of you have to understand the convention of what we are going to sort of like adhere to. Yeah, we want, okay, field from the positive charge is coming out, it's splitting out, field from the negatively charged is going to sort of converge in, and you just follow that the force is just the charge times the field. So the charge will determine the direction of the force inside that field. Sounds good? All right. There's a question comes in. If the test charge is negative, the direction will be opposite, right? Yes. Yes, opposite to the field. Exactly right. Yes. Because that negative sign will pop, will just saying that here, the negative of that Q will just saying that the F and the E will have opposite direction. Correct. Yes. Cool. Very nice. All right. So with that idea in mind, I think this is very good. And later, if you want to calculate the fields, that will be a piece of cake, because like, for example, if you go back to the previous exercise there, I can just bring back that charge. And then I can just, using the E that you just found out, multiply by the charge that you put it here. And then you can get back force equal to Q times sigma E. And you are done. Okay? All right. So I hope you see the connections between field and force today. And we're going to have more exercises for you to do next time. All right. And we will build on top of this more and more stuff that we can learn. Sounds like a good one here. All right. So any questions further? All right, guys. So if not, then I hope you learned something today, and I will see you guys on Saturday. All right, guys. Thank you very much. Take care.